Hello everyone, we are Group 19 from BTech 5th semester Computer Science and Engineering Department at GITAM. Today we are presenting a project on detecting pneumonia anomalies from X-ray images using an autoencoder, specifically a unit architecture. This project focuses on an unsupervised anomaly detection approach. We'd like to thank our mentor Dr. Santoshi Kumari for her guidance. Our project team consists of 3 members.
Hello, I'm Pravalika.
I am Bhavya.
And I'm Prakruti.
Here's a quick look at the presentation outline. We will cover the project's background, its core motivation and objectives, the tools and algorithms we used, our methodology, the model architecture, the output, the deployed front-end, the impact of our work, and finally a conclusion. The timely and accurate diagnosis of pulmonary infections like pneumonia remains a critical challenge in clinical settings. This challenge is often compounded by a shortage of expert radiologists. The primary goal of a project is to leverage deep learning to build a robust, automated system. This system is designed to quickly flag abnormal chest X-rays, thereby accelerating the screening process and providing crucial assistance to doctors. Our aim is very specific: to design and develop an unsupervised deep learning model capable of detecting pneumonia from chest X-rays using reconstruction error. The key phrase here is unsupervised, which we will explain in more detail in the upcoming slides. Our motivation is twofold. First, we want to create an accessible AI triage tool that can rapidly and reliably detect anomalies. This is critical for reducing diagnostic delays, prioritizing high-risk patients immediately, and supporting clinicians in settings where access to expert radiologists is limited. Second, we use an unsupervised unit autoencoder architecture to overcome the massive data constraints of traditional, fully supervised methods. By learning only the structure of a healthy lung, the model generates a highly sensitive anomaly score, the reconstruction error that flags any structural deviation, making it flexible and robust against various unknown pathologies. Our core objectives are to learn the structure of healthy lungs, build a CNN-based autoencoder model using TensorFlow, and train it exclusively on normal X-rays. Anomalies like pneumonia are then detected using reconstruction loss. Finally, we aim to deploy the system using Streamlit for real-time usage to help doctors prioritize high-risk patients. It's important to note that this model is designed to support doctors, not replace them. The dataset here we used here is Kaggle dataset, and here's the link of the dataset.
We use TensorFlow pneumonia classification dataset for training our model. The chest X-ray contains 3 directories: 234 normal files, 390 pneumonia files in the test directory, 1341 normal files, 3875 pneumonia files in train directory, 8 files of pneumonia and normal in val directory.
To build and deploy the system, we utilized a range of tools. Our primary programming language was Python. We built a deep learning model using TensorFlow, Keras. For image preprocessing and resizing, we used OpenCV. NumPy was essential for numerical computation. Finally, we chose Streamlit for the web-based deployment, allowing for real-time predictions, and Pickle to save our optimal threshold value. We used Pill for handling uploaded image files in the app. This slide summarizes the technical backbone of the project. For the model architecture, we used a convolutional autoencoder, specifically one unit inspired. The encoder compresses image features and the decoder reconstructs the original input. Critically, it learns representations of only normal X-rays. The main techniques involved unsupervised anomaly detection. We applied several steps of image preprocessing, including resizing to 256 by 256 and normalization. We also use Clahe for contrast enhancement to improve image quality before training. Anomaly detection is performed via reconstruction, error analysis, and a threshold-based classification. The loss function used was mean squared error. Although in the final application we used an improved SSIM plus L1 hybrid loss, the Adam optimizer was used for stable convergence, and the anomaly threshold was calculated using the mean plus k times the standard deviation of the reconstruction errors. We evaluated the final model using standard matrices like accuracy, precision, recall, and the confusion matrix. Our methodology followed a standard machine learning pipeline tailored for this unsupervised task. First, we gathered and cleaned the data, preparing it for training, which involved normalization and scaling. We then designed and trained our autoencoder to learn the normal patterns exclusively. We determined a reconstruction error threshold to cleanly distinguish between a normal X-ray and an anomalous or pneumonia X-ray. We applied the trained autoencoder on a test set containing both normal and pneumonia images to evaluate its performance against the calculated threshold. Finally, we created an interactive interface to upload data and visualize the anomaly predictions in a real-time environment. Diving deeper into the model architecture, the data preprocessing involves resizing all images to 256 by 256 and normalizing pixel values to a range of 0 to 1. We then train the convolutional autoencoder only on normal X-rays. The encoder compresses the input and the decoder attempts to perfectly reconstruct it. Because it only sees normal lungs during training, the model learns the normal pattern. During testing, an X-ray with pneumonia, which is structurally abnormal, will result in a significantly higher reconstruction error than a normal one.
Now let's look into the implementation part. So first, we are training this model using Jupyter Notebook. We have used Jupyter so that it will provide an interactive coding environment, and it will allow us to combine code, output, and explanations in one place. So basically, first we have installed OpenCV, NumPy, Matplotlib. OpenCV is for image processing, NumPy for data manipulation, and Matplotlib for visualization. Here we have done the pre-processing of the data set. Later we have trained the model using TensorFlow. And here we can see the parameters which is of the given data set, and these are the output shapes. After that, we have compiled the data set together in Autoencoder and trained it. After training it, we can see the confusion matrix, which is actually the comparison between the actual data and the predicted data. Here we can see that the actual and predicted data vary a lot. From this, we can see that there was around 99% of failures. So we have tried to maintain the threshold level. After maintaining the threshold level, we can see the new confusion matrix, where the gap between the actual and predicted data has lessened up. So after that, we have compiled the autoencoder again and trained it. Later, we have used Clahe for the image to improve the image quality. It will basically contrast the images. After doing that, we can see that the data is still nowhere to actual data. The predicted data is nowhere to actual data. So we have tried to import unit. After importing unit, we can see that the confusion matrix the gap between the actual and predicted have been lessened up. So we have used unit, threshold by maintaining the threshold levels, and Clahe all together, and then we have seen that the confusion matrix that we get after that is kind of accurate. Here we can see that the actual pneumonia cases and the predicted pneumonia cases are kind of similar. So later we have saved that and visualized it using Matplotlib. Then we have tested it with the normal images first, where we can see that it is not actually that accurate, but then when we do it with the pneumonia cases, it's around 90% accurate. So we saved it using Pickle, and Pickle will basically save the data set or the whole process that we have done, the functionalities using model.h5, and it will store the data as model.pickle. So this is what we have seen here, the model compilation and training, followed by the preparing of test data. And this is all the three confusion matters of that we have mentioned before. In the first, we have only using OpenCV, Matplotlib and NumPy, which we can see that the success rate was only 1% and the failure was around 99%. In the second confusion matrix, where we have used UNit and Clahe for improving the quality of the image, we can see it had around 20% of success. Later, by combining everything together, UNit, Clahe, and maintaining the threshold, we can see that we got around 82% of the success. This was the output that we got.
The frontend begins by importing all necessary modules. Streamlit to build the user interface and control app layout, TensorFlow to load the trained autoencoder model, NumPy and OpenCV for pre-processing and numerical computation, PIL, Python imaging library to handle image uploads in Streamlit, Pickle to load the saved anomaly detection threshold. After importing, we set the title and layout of the Streamlit page. So as soon as you run the app with Streamlit run app.py, it launches a clean web page with a title and upload section. The next step in the front end is to load the trained model and the pre-calculated threshold value. Here, the trained autoencoder model from the backend is loaded. This is what performs reconstruction. The threshold.tkl file stores the cutoff loss value that separates normal X-rays from pneumonia cases. This ensures consistency. The front end uses exactly the same parameters and logic that were derived during backend training and testing. The next part is the image upload and pre-processing workflow. The user uploads an image via a simple file uploaded in the app. It resized to 256 by 256 to match the model's expected input shape. Pixel values are normalized to the range 0 to 1. The image is reshaped to 1, 256, 256, 1, adding batch and channel dimensions before feeding it to the model. This ensures the uploaded image perfectly matches the format of the training data. Once pre-processing is done, the image is passed to the autoencoder for reconstruction. The reconstruction loss is calculated using mean squared error. It tells us how well the model reproduced the uploaded image. Now, this loss is compared with the saved threshold value. If the loss is below the threshold, the reconstruction is good, normal X-ray. If it's above the threshold, reconstruction is poor, pneumonia detected. This simple comparison allows the model to make unsupervised predictions on unseen data. Finally, the Streamlit app displays results beautifully for the user. The original X-ray and the reconstructed image side by side. The exact reconstruction loss value, which adds transparency to the prediction. Now let's see how the web application works. The web application is running on a local host. This is how the interface of the web application looks like. Now let's test it by browsing the files. First, we'll test it with normal images. We uploaded the normal image. As you can see, the diagnosis says normal. The reconstruction error is 0.00017. The anomaly threshold is set to 0.0020. And below that, there is a comparison between the original uploaded X-ray and the model's reconstruction. Now let's test it by using pneumonia X-rays. The pneumonia X-ray is uploaded. As you can see, the diagnosis says anomaly detected. The reconstruction error is 0.00024. So we came to a conclusion that if the reconstruction error is higher than the anomaly threshold, then anomaly is detected. If it's less, it is normal. Below is the uploaded X-ray and model's reconstruction as seen before. This is how our web application runs. As you have seen, this is the interface, the comparison of the normal This is for the pneumonia.
What's the real world impact of this work? It offers faster and better diagnosis. This tool can flag suspicious x-rays immediately, sometimes even before a doctor sees them, which is crucial for early detection. It's a dedicated support tool for doctors, helping them prioritize high-risk patients. And finally, it dramatically increases accessibility to healthcare, allowing areas with few radiologists to still benefit from expert-level screening. To wrap up, this project proves that AI can be truly meaningful assistant in healthcare, helping to support doctors and boost diagnostic accuracy. It's a vital step toward making healthcare more accessible and efficient, especially in areas where medical resources are limited. Thank you for watching.